Statistical mechanics is a branch of theoretical physics that studies, using probability theory, the average behavior of a mechanical system made up of a large number of equivalent components where the microscopic realization of the system is uncertain or undefined. A common use of statistical mechanics is in explaining the thermodynamic behavior of large systems. This branch of statistical mechanics, which treats and extends classical thermodynamics, is known as statistical thermodynamics or equilibrium. Statistical mechanics. Microscopic mechanical laws do not contain concepts such as temperature, heat, or entropy. However, statistical mechanics shows how these concepts arise from the natural uncertainty that arises about the state of a system when that system is prepared in practice. The benefit of using statistical mechanics is that it provides exact methods to connect thermodynamic quantities to microscopic behavior, whereas in classical thermodynamics the only available option would be to just measure and tabulate such quantities for various materials. Statistical mechanics also makes it possible to extend the laws of thermodynamics to cases which are not considered in classical thermodynamics. For example, microscopic systems and other mechanical systems with few degrees of freedom. Statistical mechanics also finds use outside equilibrium. An important sub-branch known as nonequilibrium statistical mechanics deals with the issue of microscopically modeling the speed of irreversible processes that are driven by imbalances. Examples of such processes include chemical reactions, or flows of particles and heat. Unlike with equilibrium, there is no exact formalism that applies to non-equilibrium statistical mechanics in general, and so this branch of statistical mechanics remains an active area of theoretical research. Principles, mechanics and ensembles. In physics there are two types of mechanics usually examined: classical mechanics and quantum mechanics. For both types of mechanics, the standard mathematical approach is to consider two ingredients: the complete state of the mechanical system at a given time, mathematically encoded as a phase point or a pure quantum state vector, an equation of motion which carries the state forward in time, Hamilton's equations, or the time-dependent Schrödinger equation. Using these two ingredients, the state at any other time, past or future, can in principle be calculated. There is however a disconnection between these laws and everyday life experiences, as we do not find it necessary to know exactly at a microscopic level the simultaneous positions and velocities of each molecule while carrying out processes at the human scale. Statistical mechanics fills this disconnection between the laws of mechanics and the practical experience of incomplete knowledge, by adding some uncertainty about which state the system is in. Whereas ordinary mechanics only considers the behavior of a single state, statistical mechanics introduces the statistical ensemble, which is a large collection of virtual, independent copies of the system in various states. The statistical ensemble is a probability distribution over all possible states of the system. In classical statistical mechanics, the ensemble is a probability distribution over phase points, usually represented as a distribution in a phase space with canonical coordinates. In quantum statistical mechanics, the ensemble is a probability distribution over pure states, and can be compactly summarized as a density matrix. As is usual for probabilities, the ensemble can be interpreted in different ways. An ensemble can be taken to represent the various possible states that a single system could be in, or the members of the ensemble can be understood as the states of the systems in experiments repeated on independent systems which have been prepared in a similar but imperfectly controlled manner, in the limit of an infinite number of trials. These two meanings are equivalent for many purposes, and will be used interchangeably in this article. However, the probability is interpreted. Each state in the ensemble evolves over time according to the equation of motion. Thus, the ensemble itself also evolves, as the virtual systems in the ensemble continually leave one state and enter another. The ensemble evolution is given by the Liouville equation or the von Neumann equation. These equations are simply derived by the application of the mechanical equation of motion separately to each virtual system contained in the ensemble, with the probability of the virtual system being conserved over time as it evolves from state to state. One special class of ensemble is those ensembles that do not evolve over time. These ensembles are known as equilibrium ensembles, and the condition is known as statistical equilibrium. Statistical equilibrium occurs if for each state in the ensemble. The ensemble also contains all of its future and past states with probabilities equal to the probability of being in that state. The study of equilibrium ensembles of isolated systems is the focus of statistical thermodynamics. Non-equilibrium statistical mechanics addresses the more general case of ensembles that change over time, and/or ensembles of non-isolated systems. Statistical thermodynamics. The primary goal of statistical thermodynamics is to derive the classical thermodynamics of materials in terms of the properties of their constituent particles and the interactions between them. In other words, statistical thermodynamics provides a connection between the macroscopic properties of materials in thermodynamic equilibrium and the microscopic behaviors and motions occurring inside the material. Whereas statistical mechanics proper involves dynamics, here the attention is focused on statistical equilibrium. Statistical equilibrium does not mean that the particles have stopped moving, rather, only that the ensemble is not evolving. Fundamental postulate: a sufficient condition for statistical equilibrium with an isolated system is that the probability distribution is a function only of conserved properties. There are many different equilibrium ensembles that can be considered, and only some of them correspond to thermodynamics. Additional postulates are necessary to motivate why the ensemble for a given system should have one form or another. A common approach found in many textbooks is to take the equal a priori probability postulate. This postulate states that for an isolated system with an exactly known energy and exactly known composition, the system can be found with equal probability in any microstate consistent with that knowledge. The equal a priori probability postulate therefore provides a motivation for the microcanonical ensemble described below. There are various arguments in favor of the equal a priori probability postulate. Ergodic hypothesis. An ergodic state is one that evolves over time to explore all accessible states, all those with the same energy and composition. In an ergodic system, the microcanonical ensemble is the only possible equilibrium ensemble with fixed energy. This approach has limited applicability, since most systems are not ergodic. Principle of indifference. In the absence of any further information, we can only assign equal probabilities to each compatible situation. Maximum information entropy. A more elaborate version of the principle of indifference states that the correct ensemble is the ensemble that is compatible with the known information and that has the largest Gibbs entropy. Other fundamental postulates for statistical mechanics have also been proposed. 3 thermodynamic ensembles. There are 3 equilibrium ensembles with a simple form that can be defined for any isolated system bounded inside a finite volume. These are the most often discussed ensembles in statistical thermodynamics. In the macroscopic limit, they all correspond to classical thermodynamics. Microcanonical ensemble describes a system with a precisely given energy and fixed composition. The microcanonical ensemble contains with equal probability each possible state that is consistent with that energy and composition. Canonical ensemble describes a system of fixed composition that is in thermal equilibrium with a heat bath of a precise temperature. The canonical ensemble contains states of varying energy but identical composition. The different states in the ensemble are accorded different probabilities depending on their total energy. Grand canonical ensemble describes a system with non-fixed composition that is in thermal and chemical equilibrium with a thermodynamic reservoir. The reservoir has a precise temperature, and precise chemical potentials for various types of particle. The grand canonical ensemble contains states of varying energy and varying numbers of particles. The different states in the ensemble are accorded different probabilities depending on their total energy and total particle numbers. For systems containing many particles, all three of the ensembles listed above tend to give identical behavior. It is then simply a matter of mathematical convenience which ensemble is used. Important cases where the thermodynamic ensembles do not give identical results include microscopic systems, large systems at a phase transition, large systems with long-range interactions. In these cases the correct thermodynamic ensemble must be chosen as there are observable differences between these ensembles not just in the size of fluctuations, but also in average quantities such as the distribution of particles. The correct ensemble is that which corresponds to the way the system has been prepared and characterized. In other words, the ensemble that reflects the knowledge about that system. Calculation methods. Once the characteristic state function for an ensemble has been calculated for a given system, that system is solved. Calculating the characteristic state function of a thermodynamic ensemble is not necessarily a simple task, however, since it involves considering every possible state of the system. While some hypothetical systems have been exactly solved, the most general case is too complex for exact solution. Various approaches exist to approximate the true ensemble and allow calculation of average quantities. There are some cases which allow exact solutions. For very small microscopic systems, the ensembles can be directly computed by simply enumerating over all possible states of the system. Some large systems consist of many separable microscopic systems, and each of the subsystems can be analyzed independently. Notably, idealized gases of non-interacting particles have this property, allowing exact derivations of Maxwell-Boltzmann statistics, Fermi-Dirac statistics, and Bose-Einstein statistics. A few large systems with interaction have been solved by the use of subtle mathematical techniques. Exact solutions have been found for a few toy models. Some examples include the Bethe-Ansatz square lattice Ising model in zero-field, hard hexagon model. Monte Carlo. One approximate approach that is particularly well suited to computers is the Monte Carlo method, which examines just a few of the possible states of the system, with the states chosen randomly. As long as these states form a representative sample of the whole set of states of the system, the approximate characteristic function is obtained. As more and more random samples are included, the errors are reduced to an arbitrarily low level. The Metropolis-Hastings algorithm is a classic Monte Carlo method which was initially used to sample the canonical ensemble. Path integral Monte Carlo, also used to sample the canonical ensemble. Other for rarefied non-ideal gases, approaches such as the cluster expansion use perturbation theory to include the effect of weak interactions, leading to a virial expansion. For dense fluids, another approximate approach is based on reduced distribution functions, in particular the radial distribution function. Molecular dynamics computer simulations can be used to calculate microcanonical ensemble averages in ergodic systems. With the inclusion of a connection to a stochastic heat bath, they can also model canonical and grand canonical conditions. Mixed methods involving nonequilibrium statistical mechanical results may be useful. Nonequilibrium statistical mechanics. There are many physical phenomena of interest that involve quasi-thermodynamic processes out of equilibrium, for example, heat transport by the internal motions in a material, driven by a temperature imbalance. Electric currents carried by the motion of charges in a conductor, driven by a voltage imbalance. Spontaneous chemical reactions driven by a decrease in free energy. Friction, dissipation, quantum decoherence. Systems being pumped by external forces. And irreversible processes in general. All of these processes occur over time with characteristic rates, and these rates are of importance for engineering. The field of non-equilibrium statistical mechanics is concerned with understanding these non-equilibrium processes at the microscopic level. In principle, non-equilibrium statistical mechanics could be mathematically exact. Ensembles for an isolated system evolve over time according to deterministic equations such as Liouville's equation or its quantum equivalent, the von Neumann equation. These equations are the result of applying the mechanical equations of motion independently to each state in the ensemble. Unfortunately, these ensemble evolution equations inherit much of the complexity of the underlying mechanical motion, and so exact solutions are very difficult to obtain. Moreover, the ensemble evolution equations are fully reversible and do not destroy information. In order to make headway in modeling irreversible processes, it is necessary to add additional ingredients besides probability and reversible mechanics. Non-equilibrium mechanics is therefore an active area of theoretical research as the range of validity of these additional assumptions continues to be explored. A few approaches are described in the following subsections. Stochastic methods. One approach to non-equilibrium statistical mechanics is to incorporate stochastic behavior into the system. Stochastic behavior destroys information contained in the ensemble. While this is technically inaccurate, the randomness is added to reflect that information of interest becomes converted over time into subtle correlations within the system, autocorrelations between the system and environment. These correlations appear as chaotic or pseudo-random influences on the variables of interest. By replacing these correlations with randomness proper, the calculations can be made much easier. Boltzmann transport equation. An early form of stochastic mechanics appeared even before the term statistical mechanics had been coined in studies of kinetic theory. James Clerk Maxwell had demonstrated that molecular collisions would lead to apparently chaotic motion inside a gas. Ludwig Boltzmann subsequently showed that, by taking this molecular chaos for granted as a complete randomization, the motions of particles in a gas would follow a simple Boltzmann transport equation that would rapidly restore a gas to an equilibrium state. These approximations work well in systems where the interesting information is immediately scrambled up into subtle correlations, which essentially restricts them to rarefied gases. The Boltzmann transport equation has been found to be very useful in simulations of electron transport in lightly doped semiconductors, where the electrons are indeed analogous to a rarefied gas. A quantum technique related in theme is the random phase approximation, BBGKY hierarchy. In liquids and dense gases, it is not valid to immediately discard the correlations between particles after one collision. The BBGKY hierarchy gives a method for deriving Boltzmann-type equations but also extending and beyond the dilute gas case, to include correlations after a few collisions. Celldich formalism. A quantum approach to including stochastic dynamics is found in the Celldich formalism. This approach often used in electronic quantum transport calculations. Near equilibrium methods. Another important class of non-equilibrium statistical mechanical models deals with systems that are only very slightly perturbed from equilibrium. With very small perturbations, the response can be analyzed in linear response theory. A remarkable result, as formalized by the fluctuation dissipation theorem, is that the response of a system when near equilibrium is precisely related to the fluctuations that occur when the system is in total equilibrium. Essentially, A system that is slightly away from equilibrium, whether put there by external forces or by fluctuations, relaxes towards equilibrium in the same way. Since the system cannot tell the difference or know how it came to be away from equilibrium, this provides an indirect avenue for obtaining numbers such as ohmic conductivity and thermal conductivity by extracting results from equilibrium. Statistical mechanics. Since equilibrium, statistical mechanics is mathematically well defined and more amenable for calculations. The fluctuation-dissipation connection can be a convenient shortcut for calculations in near-equilibrium statistical mechanics. A few of the theoretical tools used to make this connection include fluctuation-dissipation theorem, Onsager reciprocal relations, Green-Kubo relations, Landauer-Buteyko formalism, Morris-Wanzig formalism. Hybrid methods. An advanced approach uses a combination of stochastic methods and linear response theory. As an example, one approach to compute quantum coherence effects in the conductance of an electronic system is the use of the Green-Kubo relations, with the inclusion of stochastic dephasing by interactions between various electrons by use of the Keldysh method.